Welcome to Analytic Methods for Lawyers. I'm Professor Seth Chandler from the University of Houston Law Center, and today we're going to be taking a look at maximum likelihood estimators. Oftentimes we want to build a mathematical model that explains behavior, might permit simulation if we could do so, and a key technique for building models is to find the parameters among some pre-specified family of models that's most likely to have generated the data under study. This technique is called maximum likelihood estimation, and it's the main subject of this video. We're also going to look at how one can emulate maximum likelihood estimation using penalty functions. Okay, so let's get the concept under our belt. Supposing we see a bunch of values, maybe they're the number of hurricanes in a year, and we have some reason to think that the data could be the outcome of a Poisson distribution, which we haven't seen before, but it's just a univariate distribution, and its distribution domain are the integers greater than or equal to 0. But which member of the Poisson family could it be? And so we can use maximum likelihood estimators to help us figure it out. So let's generate the data. Here's our Poisson distribution now. In the real world, you don't see this. This is, all you see is the data, but I'm letting you in behind the curtain so you can see how I actually generated the data. And we're going to generate 10 samples. We've seeded our random number generator so that the results are replicable. And there we go. So here are the number of hurricanes in each of a bunch of seasons. Okay? So let's assume that the data comes from some member of the Poisson family. The Poisson distribution just takes a single parameter. We'll call it lambda because usually Poisson distribution parameters are called lambda. Let's figure out the probabilities of each of these hurricane events given that the parameter of the Poisson distribution was in fact lambda. So we're going to take advantage of the listability of the PDF function here. We don't have to do map. We can just basically stick all the hurricane values in here, and it automatically maps. We'll assign the results to a variable called symbolic probabilities. So there we go. It's a bunch of things with e's and lambdas and powers. Okay, so we can take the product of these. If we assume that the number of hurricanes one year is independent of the number of hurricanes the next year, which is not a great assumption in the real world, but you're going to have to indulge me here, then we can get the joint probability that we would see this combination of hurricanes over a 10-year period. So you remember apply basically replaces the head, and so we're going to replace the list head of this expression with multiplication, and it'll then just do out the multiplication. So there we go. It's some ghastly expression, but we don't really care. And we can now, you can see the only variable in this is lambda, and so we can plot this joint likelihood value over lambda, and I'll let lambda go from 0.1 to 12. All right? And so there it is. And we could then use argmax to figure out where the likelihood function is maximized. So we're going to have our syntax here. We're going to try and find the maximum value of lambda. This is what we're trying to maximize. And I do want to tell the computer that lambda really needs to be greater than 0. We don't like Poisson distributions that have a negative lambda value. So when we do that, we get 39 divided by 5, and that is our maximum likelihood estimate of the parameter lambda. Okay, so we've now seen how to find the maximum likelihood estimator of a distribution with a single parameter, where we simply have a bunch of values that we believe were drawn from some member of a distribution family. And we're going to see actually that this does have a relationship to Bayesian statistics, but for now, this is what we need to know. Remember what we did? We used the PDF function of a symbolic distribution to calculate the probabilities of each event symbolically. We multiplied all of those together to get the joint likelihood because we assumed that the events were independent from each other. And then we simply used magic or calculus to figure out where that value was maximized. Let's try something a little more challenging. Let's look at regression. Supposing we believe we have some function that maps an x value into a y value, and we think it's given by some linear function ax plus b, and that what we actually see in our data is therefore ax plus b plus some noise, epsilon, where epsilon is randomly distributed. Maybe we think it's distributed according to some normal distribution. And here is the exact data that we observe. We'll just load that in, make a little plot, and there's our data, and what we're trying to do is to basically fit a line from it. So what we want to do is to, again, compute the PDF of each y value, this time not assuming a constant distribution, but a distribution that is whose mean is a parameter of the x, whose mean is a function of the x value, and the function is therefore some linear function ax plus b. So let's just look, I think, at this code here. What we're going to say is we have a function and it computes the PDF of a certain normal distribution evaluated at y. We're trying to see how likely is it in some sense that you would get that y value. The second parameter of the distribution, of the normal distribution, stays the same. It's some value s. For the moment, I don't care what that s is. What I do care about is that the mean of the distribution changes. How rapidly does it change? Well, that depends basically on A. What's its value? What's the mean when x is 0? That's B. So the idea is that we have a PDF function that is responsive, whose distribution is responsive to the x value. And now what we're going to do is we're going to take our data and we're going to compute the PDFs for each of the points. Okay, so I'm going to do that now. And we now have a expression. There are expressions in A and B and also in S, although it's going to turn out that S doesn't matter very much. We're going to do the same thing we did last time. In order to get the joint probability, we're going to multiply each of these individual probabilities together, because we're again going to assume that the errors are independent of each other. So I'm going to multiply them, and then I'm going to simplify the expression. And here we are. We have some rather ugly looking thing in A and B. And now what we're going to do is I'm just going to set S equal to 1. It's going to turn out that it doesn't matter very much. And what I'm going to do is I'm going to make a plot of this joint likelihood function, of joint likelihood expression. I'm going to make a 3D plot as A goes from 2.8 to 3.5 and B goes from 2 to 4, and there's some cosmetics here that I've iconized away. All right, and there we go. So here's our picture. And so what we can now eyeball is that the joint probability appears to be maximized, maybe, I don't know what that is, maybe 3.2, 3.0, something like that. And we can see that the likelihood falls away as we depart from that. And if we look at this from on top, we can kind of see that they seem to be elliptical contour lines, that there's some sort of ellipsoids of constant likelihood. Okay, but we can do better than eyeballing. And what we're going to do is we're going to, first of all, use our D function, which I hope you remember from one of the introductory lectures, is something that calculates the derivative of an expression, the slope of an expression. And one thing we know about mountains is that mountains, smooth mountains, have zero slope at their peak. Why? Because if they didn't have zero slope, you could move up the slope, okay? And get to a higher point. We're going to try to find out when is the derivative of this joint likelihood function 0 in the A direction, going this way or that way, and when is it 0 going in the B direction, going this way. And if we have both of those conditions, we know we are at a local extrema of the function, assuming continuity and some other icky things. All right, so what we're going to do is we're going to calculate that. We're then going to stick those equalities into a pipeline where we first solve it for A and B. I'm going to tell it to not produce various warning messages, and then I'm going to take the first solution because it turns out there's only one solution and we don't need to clutter our minds with other things. So here we go. All right, and what we find out is that it's maximized when A is 3.10536 and B is 3.20691, or we could use the n maximize function, which says, look, find me where this is maximized. And by the way, do you see here, I haven't said anything about S here. I have not, that when I calculated joint likelihood, I left S in. This is why I say S doesn't really matter. No matter what S you pick, you get the same thing. So I'm going to say, look, maximize the joint likelihood. The only thing I want is for you to know that S, which is that standard deviation of our normal distribution up here, is positive because you can't have negative standard deviations. Find the values of A, B, and S that maximize that likelihood. This is a little bit on some options to n maximize, and if we do that, we get exactly the same thing. Okay? So the values we just discovered for A and B are called the maximum likelihood estimators of those parameters. We found those parameters by computing a joint likelihood function and then by finding what values of A and B maximize those. And in fact, now what I'm going to do is I'm going to produce another little graphic that shows the optimal point overlaid over our data. And here's our best fit. Okay? And it looks pretty good to me. You can kind of see that it certainly seems like a reasonable fit. What we just did was maximum likelihood estimates for regression given what's called homoscedasticity, which means that the noise is constant. That is, if we look at our expression here, what we see is that this x is independent of x. The spread of noise doesn't depend on the x value. Now, in many settings that may be true, but there are other settings in which the distribution of noise, for example, might grow as x gets bigger, or it might have some really funky relationship to x. And what we want to be able to do is to be able to perform maximum likelihood estimation, MLE, in settings where the noise is functionally dependent on the x value. Here, with this homoscedastic regression, only the mean depended on the regression. But maybe we want to have settings in which the standard deviation of the noise depends on the x value as well. So this is called heteroscedasticity, and what we're now going to look at is an example of that. So now let's assume that instead of this being this noise term just being s, it's some constant s multiplied by x squared. Okay, that the noise is proportional to the square of the x value. Okay? So what we're going to do is, this is our same computation as before. We're going to compute the symbolic PDF using a symbolic normal distribution, and apply it to our data points and try to get the PDF values for the y value. Okay? So now those are our probability or our likelihoods of each individual point occurring given values for A, B, and S. And now what we're going to do is we're going to form a joint likelihood by multiplying those probabilities together. We're allowed to do that because we believe that the errors are independent of each other. We get this rather ugly expression. And now what we're going to do, though, is we're simply going to say, hey, Wolfram, you're good at figuring out maximums. I want you to find the maximum, the values of A, B, and S that maximize this expression. And the only thing I want to make sure you understand is that S needs to be greater than 0. Again, I'm going to give some instructions to the maximizer just to make sure it does a good job. And we do that, chunk, and it's going to tell me that this is the best fit here is when A is 2.59, B is 3.44, and that S thing is 0.37. So what I now want to show you is that that gives us a different estimate of the best fit line than when we assumed that the model was homoscedastic, that the spread of noise didn't depend on X. So let's see, the red line is the line we computed earlier, and the green line is the line that we're fitting now. So what this tells you, I'm not so interested in the specifics here. What I'm interested in you grasping is that the best fit, which may be used in some litigation context to prove something about some relationship, that depends on the noise model you select. And if the noise model isn't sensible, doesn't have some basis, then you can get an answer which isn't quite right. Now here, the difference to me, doesn't look huge, but it might make a difference in other cases, or maybe we do need some precision. Was the slope really this big, or was the slope really only this big? So that is maximum likelihood estimation under assumptions of heteroscedastic noise. And I want to impress upon you again that noise matters. Your noise model matters. Okay, if you ever look at literature on MLE or see professionals doing MLE, you're likely to see a discussion of log likelihoods. And I want to explain now why that's used. And the short answer is that the sort of problem I just solved, while you can do it when you have a few points, when you have a lot of points, you can start to get numeric errors in your computation. And therefore, use of log likelihoods avoids these numeric errors, and that's one of the reasons that they are used. The general subject here has to do with monotonic transformations and optimization. So here's the idea. Supposing you have some function f, and that function is maximized at some value x. Okay, I don't really care what the function is. All I'm going to tell you is that there's some value x that maximizes the value of that function. Now, compose that function with another function g, that is, take the output from f of x and make that the input to another function g. And the only restriction on g I'm going to impose is that it's monotonic. That is, if it goes up at any point, it never goes down. And if it goes down at any point, it never goes up. And here's what I contend. I contend that that same value x that maximized f also maximizes g of f of x, of the composition. And therefore, if it's easier to actually work with g of f of x than it is to work with f of x, so long as g is monotonic, you are free to do so in an optimization problem. So before I explain further, let's take an example, okay? Supposing our first function f is, it takes 5 and it subtracts from that x plus 3 squared. And we can make a little picture of that. All right, there it is. And we can now tell our friends at the kernel to maximize it. So we do. And we get that it's maximized at -3, and perhaps some of you can intuit why that is. Now, the function x cubed is monotonic. It looks like this. So let's compose it with our function f. Okay, here's g. And now I'm going to say I want you to take f of g of x. Okay, remember that slash star means and then. All right, so let's run that. And that's, okay, that's because I didn't evaluate this cell first. And now, there we go. So that's the composed function. And now let's actually plot the composed function. Okay, there's our composed function. Let's run argmax on g of f of x, and probably for notational consistency, I ought to write it this way. And it's -3, okay, which is the same thing we got up here. So that doesn't prove my point, but it at least illustrates my point. There's actually a fairly simple proof that I think will help you understand why monotonic transforms preserve order and why what we just did works. So supposing you've got a monotonic upward sloping function. And what that means is that if x2 is bigger than x1, then g of x2 must be bigger than g of x1. But this means that if a point f of x2 is higher than a point f of x1, then g of f of x2 must be greater than g of f of x1. So if there is no value x2 such that f of x2 is greater than f of x1, there's an extra bracket there, then it must be the case that there's also no value x2 such that g of f of x2 is greater than g of f of x1. And so if you've found the maximum and it's f of x1, then g of f of x1 must be maximizing g. And if you have a downward sloping function, it's essentially the same argument. So I don't know if that helps or not. You can either take it on faith or you can try to understand the proof. But either way, if you have a function and you compose it with a monotonic function, then the value that maximizes the composed function also maximizes the original function and vice versa. Okay, so with that in mind, there's a specific monotonic function that I have very much in mind to use here, and that's the log function. Log is defined on all positive values, so it's going to work just fine on probabilities and PDF values, so long as they're not 0. And so if some parameter p maximizes the product of some probabilities or likelihoods, that same parameter p must maximize the log of the product of the probabilities. But, and this is where the computer gets very happy, the log of a product, at least of real numbers, is equal to the sum of the logs. And so, in the real world, what people do, instead of maximizing the product of the probabilities, you maximize the sum of the log of the probabilities. And in fact, it is more traditional to minimize the negative sum of the log of the probabilities. But that last point is just a bell and whistle. The key point for you to understand is that what we're going to do now is to maximize the sum of the log probability. So let's take that original example involving hurricanes again. And we've got a symbolic Poisson distribution. We're going to take the PDF of that over all hurricanes, and then we're going to take the log of this, okay? So what we get is instead of 1 over 24 e to the negative lambda, lambda to the fourth, we get log of 1 over 24, blah, blah, blah. Okay? So basically, we've just stuck a log in front of our former PDFs. And now, let's add up all of those numbers, those logs together, and we'll just expand the result, and we get an expression in lambda. And it's kind of an icky lambda, but it turns out I can use some calculus and algebra to find out where the log likelihood, the total log likelihood is maximized. And so we'll just do that. And it turns out to be 39/5, which is exactly the same number that we got up here when we weren't using this log transformation trick or method. Okay? So back down we go. And indeed, as it turns out, in more recent versions of Wolfram language, you can save yourself some trouble. There's a function log likelihood, which just computes exactly what we've been doing. And so if I just now take the derivative of the log likelihood of the Poisson distribution of lambda with respect to hurricanes, and I take that derivative with respect to lambda, I find out for what value of lambda is that 0. Ta-da! And as I mentioned, it's more traditional to minimize the negative log likelihood, and so it's exactly the same thing. I just showed you how to do regression the right way, using maximum likelihood estimation. And I showed how we can avoid some numeric errors that might otherwise occur by maximizing the log likelihood of the probabilities. However, sometimes this can actually get quite difficult, and there's an alternative approach which is based on a loss function. Sometimes, not always, you get the same answer as you would if you'd used maximum likelihood estimation. And if you choose a good loss function, you're going to get a lot closer to the MLE answer. But oftentimes use of a loss function is simpler in terms of computation. But if you see someone using a loss function, or in fact, if you see them doing a regression or other statistical analysis, it's fair game to ask whether a maximum likelihood estimation method has been used, and if not, why do they think that their penalty method gets something close to the same answer? If it doesn't get close to the same answer, then that's a basis for criticism of their regression or other statistical method. Now, a classic method is to punish values according to their distance from the value estimated by a model. That is, we're going to compute the true value, and we're going to compute what our model says, and we're going to compute the distance between those two. And what do we mean by distance? Well, oftentimes what we mean is the square of the residual. Not always. There are lots of other distance metrics that can be used. That, in fact, there's one in particular that we will use, like cross entropy. But oftentimes you're going to try to you're going to measure the distance as the square of the residual. So let's look at this. Okay, let's apply ax plus b, a symbolic expression, to our original data. You remember, here's our data. Let's just refresh ourselves. There it is. Oops, it's off your screen. Okay, and let's just apply ax plus b to that data. Okay, so these are the values that we get. And now what we want to do is we want to take these symbolic y values and subtract from them the true values, right? What's data all to? Let's just refresh ourselves. That's those points, and if I look at our data, you can see I'm just taking the last value of each point, okay, etc. So what I'm doing is I'm taking the difference between what our model predicts symbolically and reality, and then I'm going to take, remember power total, that's a resource function that with no argument right there takes the sum of the squares, and we'll call that SST. Okay, so we now have an expression in A and B that represents the sum of the squared residuals. We can plot this as a function of A and B. That's all that's in here. So let's plot it as A goes from 2 to 4, B goes to 0 to 6, and there we have it. So now what we want to do is we want to find the values of A and B that minimize the sum of the squared residuals. And I am actually unhappy with this plot. Let's uniconize this. And what I have not done, I've told you that you really should have labels on your plot so that it's more self-contained. Right. I'm much happier with that. Let's go back and re-iconize it so that future generations will not see the clutter. Okay. Now let's evaluate it. And now you can see how the sum of the squared residuals relates to A and B. And by the way, this just means it's clipping. It's actually going higher. It's just not showing it. But looks to me like somewhere around there is the A and B values that minimize the sum of the squared residuals. I'll just ask Wolfram if we wouldn't mind computing at what values of A and B the sum of the squared residuals are minimized. And it's at 3.10, 3.20691. Now, where have we heard those numbers before? And look at this. Same numbers, okay? So it turns out that if you have homoscedastic noise, and several other assumptions are made, that minimizing the sum of the squared residuals is equivalent to a maximum likelihood estimate. That doesn't mean that's always going to be true. If I have a heteroscedastic noise, this is not going to give me the right answer, and I may have to come up with some other penalty function to compensate for that, maybe something with weights, for example. We could try other penalty functions, by the way, like supposing instead of taking the sum of the squared residuals, as I did here, I took the sum of the absolute values of the differences between the predicted value there, and the actual value there. I took the absolute value of each of them, I added them up, and I said, now tell me what values of A and B minimize that. And you can see, I mean, it's not wildly different, but it is different. And so using a different penalty function can affect the outcome. I've got one other thing I'd like to show you at this time. I guess I regard this part of the video as optional, but if you're kind of following along here with maximum likelihood estimation, we can actually learn something about logistic regression with everything we've got. So supposing we've got a function that produces output of either 0 or 1, and therefore here's our data. Okay? And you can see the y values here are all 0s or 1s, x values are all over the place. We can make a plot of that. There's our data. And we believe that the underlying model is logistic. That is, the actual values, 0 or 1, are draws from a Bernoulli distribution. You remember that's our coin flip, whose single parameter p is actually a function of two parameters, a and b, that we have to figure out. And just so you understand what does the logistic function look like, I think I've talked about logistic sigmoid before, but here we go. Let's plot this as x goes from -3 to 3. Okay? And so that's what it looks like. It's kind of sigmoid shaped. I could look at what 2x plus 5 looks like. And you can see here, in order to see it fully, I better go back to -7 or something. You can see that it's kind of shifted to the left. So what we're trying to really guess is we think this is coming out of a Bernoulli distribution where the parameter is a function of x, but it's also a function of two things we're trying to optimize, A and B. Okay? So I think if we actually look at the code here, it might be clearer. What we're going to do is we're going to take our data with its x and y points, and for every point, we're going to compute a symbolic value, ax, a times the x value, plus b. We're going to take the logistic sigmoid of that, and then we're going to say that that gives us a Bernoulli distribution. We're going to compute the PDF of the Bernoulli distribution at y. And that's going to give us the likelihood that a particular y value would exist if the underlying distribution was a logistic sigmoid of ax plus b. So I'm going to do that in this part of the code here. And then what I'm going to do, in fact, let's just break that out so you can see what happens. All right, so we get some expression here. It seems to have a lot of a's and b's in it, but the x's and y's are gone because the actual values have been substituted in. What I'm then going to do is I don't want to try and maximize this. I want to try and maximize the log likelihood. So what I'm going to do is I'm going to take the log of all of these things and then take the total. So there we go. There's our expression. I guess it was in the notebook in advance. We can plot the negative of the logistic log likelihoods. I'll let A go from -2 to 2, B go from -2 to 2. And you can see that this likelihood, or negative log likelihood, seems to have some minimum, I don't know what that is. That's probably negative, it's probably A is 0.4 and B is -0.25. And while you're doing that, again, I'm going to fix this. I don't like that I didn't include my axis labels. That'll give you some additional time to ponder. Okay, and now what we can do is we can go back and re-iconize, and we'll just reevaluate it. All right. Let's use argmin now to figure out the values of A and B that minimize the negative log likelihood, or logistic log likelihood here. So we'll just run this code, and it looks like it's minimized when A is about 0.384 and B is about -0.237. So what we can now do is we can overlay our best fit onto our data, and you can see our best fit. So here's the code to do it. It's a little bit inscrutable. Remember, show combines two graphics. This is our earlier plot of the data here. But what's this? And the idea here is, look, I have a logistic sigmoid of AX plus B, but I'm going to plug in a rule. Let's just evaluate that rule in place. To evaluate something in place, you select it, and you hit Command Return or Apple Return, and you can see that it's now going to, that's what it's actually going to do. I'm going to revert back to the earlier code. This is a little more elegant here, but at least you see what's going on behind the scenes. I run that, and there's our picture. That's our best fit. And granted, it's not a very good fit, but on the other hand, our data is very noisy, and we don't have very much of it. So that should give you an understanding of maximum likelihood estimation. It's usually kind of a gold standard in statistics, because what you're trying to do is you've got some data and you want to figure out what is the most likely model that fits that data. Sometimes it gets more complicated than that, but that's at least a good start.